morning. Today we'll discuss about three-phase AC circuits, and in that one we will be discussing what actually star connection is and what actually delta connection is. In the last lecture we have seen an introduction to three-phase circuits. We have seen what actually balanced and unbalanced systems are, and we have also seen what do you mean by line quantities and also phase quantities. And we have also seen how three-phase AC voltage were generated, and at the end we have seen the advantages of three-phase AC when compared to single-phase AC. And in today's class we will see more about star and delta connections. I hope by the end of this lecture you will be able to derive the voltage and current relationships of line and phase values in balanced star and delta connected networks. I hope by the end you will be able to identify what is your required connection, whether it is star or delta, if you do have any specific application. So I'll start with first of all the star connection. I'll explain what actually star connection is, and then I'll show you the different quantities which will be there in star connection, and then by the help of some phasor diagrams we will try to determine the relation between line quantities and phase quantities in a star connection. So to start with the three-phase star connection, which is widely used in electrical circuits. In a star connection, the similar ends of the three windings, they will be connected to a common point which we call it as a star or neutral points, which means that if we do have three phases, let us suppose this is 1, this is 2, this is 3. The way how these three are connected, see, these ends they will be left open for your further connection, whereas these ends they will be joints. So either start or finish, any of these ends, it will be connected to one common point. So this is connected to one common point, and this particular point is called as neutral or star point in some textbooks. Okay. Now the three line conductors, they will run from the remaining three open terminals. Now these are called as line conductors. And these will be given to your external supply, or they can be given to your external load or for your external connections. Okay. And sometimes you can use a fourth wire from this neutral point also to give to your external connection. Okay. So if you use a neutral wire, then it is called as a three-phase 4-wire system, or otherwise it is called as a three-phase 3-wire star connected system. And thus the extra wire, the fourth wire, refers to the neutral wire. Okay, this is what I have mentioned here. See, the three line conductors run from the remaining three free terminals. These are the line conductors. And this system is called as three-phase 3-wire star connected systems. However, sometimes a fourth wire is carried out from the star point to the external circuit. We call it as a neutral wire, and it forms the fourth wire of your three-phase 4-wire star connected systems. Now this is a connection. See here. Now let us suppose this is one coil, this is another one, this is another one. See, if I take the first coil as A1, A2, the second coil as B1, B2, and third coil as C1, C2. See, 3 points, 3 ends, one each of these coils. It has been joined, A2, B2, C2. The remaining terminals, now they are left open for connecting with the external circuits. So this point is called as a star point or neutral point. If you want, you can run a wire from this point to your external circuit, and we call it as a neutral wire. Okay. Now, the voltage across each of these individual phases is called as your phase voltage. Okay, so this is one phase voltage, and this is one phase voltage, and this is another phase voltage from this point to C1 to C2. Now this is main line, this is main line, this is main line. Now If you want to measure the voltage between main lines instead of the phases, it is called as line voltage. See here, this is phase voltage from phase to neutral, whereas this is between the line to line. It is called as line voltage. Okay. So in the figure, now if you see finished terminals A2, B2, C2, they are connected to form a star or neutral points, whereas the remaining connectors, the points referring A1, B1 and C1, they are named R by B and they run from the remaining three terminals. Okay. So the current which is flowing in each of these circuit is called as a phase current, and the current flowing through each line connector is called as a line current. Similarly, the voltage across each phase is called as phase voltage, and the voltage across two line conductors is known as line voltage. See here, this is here phase voltage. From line to neutral. But whereas if I take from line to line, it is called as line voltage. See, this is R line, this is Y line. So this is VRV. This is line voltage. They will be having three sets of line voltage. This is between RY, and this is between YB, and this is between V and R, B and R. So R, Y, B, RY, YB, and BR. Okay. So VRY, VYB, and VBR. These are the line voltages. Whereas the phase voltages, see here, one is R with respect, I will take this point as N. So it is VRN, VYN, VBR. Okay. So these are the phase voltages. Now, what is the connection between star connection? What is the relation between line voltage and phase voltage? That is an important question. Now, if you carefully see, my line voltage VRY is not equal to VRN. If I take VR, it is not equal to VR, right? So now I'll consider this mesh now. I'll show you. Yeah. See, this is phase voltage. This is line voltage, right? Only magnitudes. The angles will be separated by 120 degrees. Okay. Try to remember that one. Okay. Now, I'll draw it here again. Right. Now, this is VRY, right? This is VRN and this is VY, right? Now, if you take this loop and apply a mesh analysis, I am applying a mesh analysis here in this particular loop. Okay. See now how the sum of all the voltage is equal to 0, right? So if I start from here, if I start from top left, it is VRY plus VYN minus VRN is equal to 0, isn't it? So if I write it in this fashion, this is my equation. Do remember these are all vectors. These are all vectors. Now let's try with the phasor diagram. Now, how to draw the phasor diagram for this one. Now let me do one thing. Now let me take an empty figure. Now what I said is VRN, VYN, VBN are the phase voltages, right? And VRY is VRN minus VYN, right? Now these are all voltages which do have a phase angle. So now I am trying to draw a phasor diagram. See VRN, if I take this as VRN, which is equal to its magnitude is, I'll take it as V phase, and its angle is 0 degrees. Now how VYN will be? VYN will be at 120 degrees. This is VYN. Its magnitude will be the same, but angle will be separated by 120 degrees. Now this is my VBN. It is minus 240. Okay, it is minus 240. Now if I want VRY, this is a line voltage, which is equal to VRN minus VYN. So I'll write it as VRN plus minus of Vyn. So which means that I should get, this is Vyn, this is minus Vyn. Right. Now see, if this is 120, this angle will be equal to defaultly 60 degrees, right? Now what I should do addition of these two vectors, Vrn and minus Vyn, right? In this case, so how to add? This is parallelogram law of addition. So this is my Vry. Now both are equal, right? So the angle will also be perfectly half, so it is 30 degrees. So this is my line voltage. If I take its magnitude as L, VL, its angle will be 30 degrees ahead of the corresponding phase voltage. Am I clear? Now if I take VYB, it will also be just like VYN plus minus VBN. So this is Vyn. What I should add with this one? Minus VBN. So minus VBN will be something like this. Right. So if I add these two, so this is my Vyn. Right. So what is its angle? This is 30. So from 120 means it will be 90 degrees, right? So this will be 30 degrees, right? So now, if I want VBR, this is VBN plus minus of VR. This is minus VR. Right. So if I join these two, this is VBR. Right. So this is the way how we draw the line voltage and also the phase voltage. Now if you carefully see, this is Vrn, this is minus Vyn. Now if I join these two, I am getting Vry. What is its magnitude? Its magnitude, see, both these vectors are same in magnitude, right? Each value is V phase and V phase. But what is the angle between them? It is 60 degrees angle between them. You know that in a vector, V1 square plus V2 square plus 2V1 V2 equals 5, where phi is the angle between the two vectors. This is the resultant of two vectors. Now if I do it, what I'll be getting, see here. This is V phase magnitude. For the second one, it is also V phase. 2 V phase, V phase. Angle between these two, these vector, is 60. Cos 60 is 1 by 2. 1 by 2 into 2 is 1. So this will become so I'll get root 3 V phase. So which means that its magnitude is root 3 V phase. If these both quantities do have V phase magnitude, then the line resultant one will be having root 3 V phase as a magnitude and its angle is 30 degrees. Understood? So for your sake, I'll draw it again. Now see here. So now see the voltage relations. As already said, to return them in the magnitude, we should go with the parallelogram graph. And see here. This is the way how we simplify the things. This is what I have done so far. Right. You can see it in the PPT. But let me explain it. Let me draw this figure once again clearly for you. Okay. Now, this is your Vrn, which is equal to V phase at an angle of 0. This is Vyn, which is V phase at an angle of minus 120. And this is your VBN, which is equal to phase voltage at minus 240. Now what is Vry? Vrn plus of minus Vyn. This is what we have done in the previous slides. So Vyn is being brought back. This angle is 120, so defaultly it will be 60 degrees. Now these two, this is minus Vyn. These two are to be joined. This is here Vry. And see the angle it is having 30 degrees angle. So if it is 0, then its angle will be 30 degrees. And what is its magnitude? That is what we have tried earlier, and it is root 3 V phase. So line voltage magnitude is root 3 times that of phase voltage, and the angle is 30 degrees ahead of phase voltage. Similarly, for YB, so VBN should be brought back, and if I join, then this is VYB. See what is its angle? Its angle is also a line voltage, root 3 phase angle, 30 degrees ahead of this one. This is minus 120, so 30 degrees ahead is minus 90. Similarly, VBN minus VRN. So it is VRN minus VRN, and if I join these two, okay, this is my VBR. It is root 3 V phase. It's an angle of minus 240, ahead 30 is minus 2. Right. This is the right. Now this is about line voltage. So what I can write here? Line voltage magnitude is root 3 times that of phase voltage magnitude. Isn't it? Whereas angle, line voltage, they lead phase voltage by 30 degrees. Right. So this is regarding the voltage. Now coming to the currents. Now let's get back to the currents. Currents will be, I'll assume that my currents lag, see these are phase currents, okay, lag phase voltages by 5. Okay, so now I'll take IR, IY and IB, these are the phase currents, and they are lagging the rest. This is a phase voltage, right? So this is phase current IR 5, and this is one more phase voltage, so here this will be IY, and this is VB, so this will be IB. Understood? This is how the phasor diagrams are drawn. And one more thing is, see, in a balanced star connection, in the previous figures, you can see that line currents are same as that of phase currents. Now I'll show you the figure now. Now this is your line voltage, right? Whereas this is your phase voltage. Phase voltage and line voltage are not the same. Both are different. See, this is only up to this one, whereas this is for both these two, you are getting line voltage. But whereas coming to the currents now, you see, this is your main line currents. And see, this is your the same current which you are getting in the line, it is passing through this individual phase. But here, in this phase, voltage is not equal to voltage across the lines. So that's why, since the same current is flowing into this phase, R phase, in the entire R phase, the same current will be flowing. Here, IY will be flowing in the entire Y phase. B phase, entire current will be flowing. And the sum of all currents must be equal to 0. Because at this point, nodal analysis, all are incoming currents, and summation must be equal to 0. And also, most important thing, line currents are same as that of phase currents. This happens only in star connection. Okay. Now, what is the power consumed now? See, the power consumed in three-phase balanced star connected circuits. Now I do have cos phi, which I call it as power factor. Try to remember, it is the angle between phase voltage and phase current only. Angle between phase voltage and phase current. Now what is P now? P, I call it as an active power. So it is, since I do have three phases, 3 VPH, IPH, cos phi. isn't it? Now I can write this one as root 3 into root 3 V phase into I phase into cos phi in star connected circuits. What is root 3 V phase? It is VL. I phase is IL. So I can write it as, and its units are watts. Similarly, Q, which is reactive power, we will be getting sin phi, root 3 VLIL sin phi. Its units are var. Finally, complex power or total power or whatever you call it as, yes, measuring VL. Understood? So the key points to be remembered. Line voltages are always 120 degrees apart from each other, and line voltages are 30 degrees ahead of their respective phase voltage. An angle between line currents and corresponding line voltage is 30 plus 5. See, I already told you. This is IR, this is VRL, and this is VRY. This is phase voltage, this is line voltage, this is current. The angle between them is 5, the angle between them is 30. This is phase current and also line current also, both remains the same. So now, what is the angle between phase voltage and phase current? It is 5 only. But line voltage and line current, what is the angle? 30 plus 5. Okay. And line voltage magnitude is root 3 times that of phase voltage magnitudes. And line current and phase current, both are same in magnitude and also angle. Try to remember these points. This will be helpful for you while you are doing the problems. Okay. So with this, I'll stop this star connection. And in the next video, we'll discuss about delta connection. Okay. Thank you.